So welcome everybody. Thank you for joining us today. This is our monthly Climate Connection series with our carbon talks, kind of a mix for this month. We're really excited about the conversation today. Our focus is carbon, but we have a sub-focus of methane today, so it's going to be very interesting. So as always, we like to do our land acknowledgement. So with gratitude and respect, we acknowledge that the lands on which Foresight operates are the traditional, ancestral, and unceded territories of the First Nations, Inuit, and Métis people. And personally, I like to acknowledge that I'm on the land of the Haudenosaunee and Anishinaabe peoples that continue to live and work here today. Please feel free to also put your land acknowledgement in the chat. So what is climate connections? The climate imperative presents enormous challenges for industries that must now align their strategy and operations with the goal of a low carbon economy. As industry steps up to meet these pressing new climate challenges, there are exciting new opportunities for the translation of research into impact. Enter Climate Connections, our problem-driven event series that connects solution seekers from industry with researchers and innovators from academia, and fosters cross-sector connections to address the climate challenge. This series brings together industry experts who present short reverse pitches on the challenges that they see. Through structured conversations with academic researchers, innovators, and entrepreneurs, we unpack and explore their challenges and hope to spark ideas and connections among the audience. And we'd love to shout out our partners. So thank you to Entrepreneurship at UBC, Simon Fraser University, and the Impact Investing Hub at the University of Victoria. We are very proud of the academic partnerships we have in this event, and we have many more collaborations in promoting these events. In order to meet our climate commitments as a country, we will need new solutions, and we are very excited to be engaging with the thousands of super bright and talented researchers across these organizations to make sure they are working on the most pressing challenges facing the sustainability of the industries that underpin our economy. These institutions represent over 100,000 students and tens of millions of dollars in equipment that we need as part of our transition. I'd like to thank them for helping make sure we have a full room today. So thank you again to Entrepreneurship at UBC, Simon Fraser University, and the University of Victoria Impact Investing Hub. So just a quick note on our agenda. I'm going to run through our welcome and intros. We're going to start with our industry experts and their panel, and that will be moderated by Brianne O'Reilly. Very excited about that. We will have a moderated Q&A, so if at any point you have a question, please feel free to drop that in the chat and we will add it to our list. And then we will have some really quick closing remarks at the end. So a little bit about Foresight. For those of you who are less familiar with Foresight, Foresight is Canada's clean tech accelerator. Our big, hairy, audacious goal is that we see Canada becoming the first G7 country to achieve net zero. To do this, we bring partners together to identify, commercialize, and adopt the clean technologies needed to address today's most urgent climate challenges. Using our Helix 5 model, we bring together industry, government, academia, investors, and innovators to address today's most urgent climate issues and support a global transition to a green economy. And we'd like to note that there are many folks from the Helix 5 model represented in this event today through panelists and audience members. Thanks for being here with us. And with that, I'm going to pass the floor over to Brianne. So Brianne O'Reilly is the Director for Program Development and External Relations for Carbon Management Canada, providing strategic oversight for the organization. Brianne manages communications projects to ensure, engage and educate stakeholders on industrial emissions reduction solutions. Brianne leads the Canadian CCUS Research and Technology Network, providing innovators in industry with efficient, coordinated, and collaborative access to Canada's world-class CCUS technology, commercialization infrastructure, and expertise. The network brings together like-minded organizations with expertise, facilities, and equipment to help demonstrate, scale, and validate technologies. She also oversees the carbon tech team, conducting industry and government outreach and providing project management expertise to support the advancement of CCUS technologies. And on top of all of that, she is the director of our Carbon Next program, which is a partnership program between Foresight and CMC to advance CCUS technologies and support industry adoption. So we're very excited to have Brianne here today, and I will pass the floor over to you.
I would like to start by saying that we are based in Calgary, myself, Brendan, Adam, and Wayne-ish. And so I would like to take the opportunity to acknowledge that we're on the traditional territories of the people of the Treaty 7 region of Southern Alberta, And the city of Calgary is also home to Métis Nation of Alberta Districts 5 and 6. And in addition to all the pieces that Shannon said, I am also the program director for the Alberta Methane Emissions program. So that is sort of how we came to talk about methane today. I'm excited to have our panelists here, Brendan Morehouse, Adam Heyman, and Wayne Hickman. And I'm going to start by turning it over to Brendan to walk us through some of the methane modeling pieces from highway emissions.
Thanks so much, Brian. That's fantastic. I think I did. I put some slides together, so maybe if we just transition to those. I have 5 minutes to tell you all why simulation modeling is good, and then 5 minutes to tell you why simulation modeling can sometimes have some problems. So next slide, please. Okay, so why simulation modeling? This is what I'm here to talk about, and I want to give a bit of background first. So the awareness of the impact of methane emissions in the oil and gas industry and how significant that impact is a relatively recent thing. And with that relatively recent awareness, there's been just an explosion in innovation in methane detection and quantification technologies. I've mentioned on screen here, we have over 200 of these unique solutions available. And yeah, they cover a really wide range of spatial and temporal resolutions, and also the data products that they can give you. So at a high level, what these are doing is they're flying over or continuously looking at or driving by oil and gas sites to look for methane emissions. And I'm going to focus on fugitive methane emissions today, also known as leaks. So when something goes wrong, methane goes up into the air and it's not supposed to. Next slide, please. So there's been this explosion of innovation in the technologies, satellites, planes that fly over and look with LiDAR sensors, drones that fly around the sites, laser-based continuous monitoring systems, etc. But there's no silver bullet. There's yet to be a technology that's the perfect one. Let's all just do this. This is the best thing for looking for methane emissions. That doesn't exist. They all can fit within a given infrastructure and the given needs of a different leak detection and repair program, which is sort of a universal term for the holistic program that an operator would adopt to look for these methane emissions. So you have all these technologies, you have all these different types of asset bases, you have all these different ways you can apply the technologies. How do we compare them? How do we find what's best for a given asset base based on constraints and cost considerations, etc.? Lots to think about. And that's where simulation modeling comes in, and where it's come in pretty extensively in the last 5 years or so. It's a really effective way to compare these technologies and the LDAR programs that they are a part of. So next slide, please. Cool. So I'm going to be talking about the leak detection repair simulator. That's the open source simulation model that Highwood Emissions uses primarily, but a lot of these ideas can be sort of expanded to other simulation models that people have been using. So on this slide, I'll go pretty quick here, but on the left is what we refer to as our virtual world. So in our simulation model, we're modeling an oil and gas infrastructure, and that's our virtual world. That's all the little sites that exist in the real world. Those are represented accordingly in the model. And so anything that's sort of going into that virtual world are the inputs into the model that informs how it behaves. So some important things are, where are the sites? What's the weather like at the sites? That can have a big impact. And then two really important IDs are, what are the emissions like at the sites? What are the routine or allowable or venting emissions? And then what are the fugitive emissions like? Leaks, again, things that shouldn't be happening. We apply leak detection and repair programs to that virtual world, and we see how much methane we can mitigate. How many leaks can we stop? There's a few sort of pieces that go into a leak detection and repair program, but at a high level, we're thinking about how is the technology used, what's the cost of the technology, and how good is the technology at seeing methane leaks. So next slide, please. So what I'm showing on screen is sort of a typical output from the simulation model. This is a really effective way to see how much methane are we mitigating? How many of these leaks are we stopping and we're saving that from going into the air? So we've modeled sort of three really sort of generic leak detection repair programs. One is based on flying a plane over your sites 12 times per year. The middle one is based on doing optical gas imaging surveys. That's a camera that you can use with on the ground. You can see leaks with it because methane's invisible to the naked eye without the camera. And then we're also comparing it to the same sort of plane-based screening, but only 4 times per year. So takeaway here, you fly planes a lot of time, you get to mitigate a lot of methane. It's the biggest bar. Next slide, please. Another great takeaway from the model, though, is we'd like to try to think about cost too. Everyone is front of mind for a lot of people. So what we're seeing here is that 12 times per year monthly plane-based program, it's really expensive. So this is just a sort of a snapshot into the pros and cons of the different programs and all the things that operators might think about when using the simulation model to compare these different programs. Next slide, please. Everyone's favorite quote about models. I'm talking about simulation models, but this is models in general from my boy, George Box. They're all wrong, but some can be useful, which does hold true here. So I want to talk about a few cases where all the models we use for methane emissions could be wrong. Next slide, please. I think this is a pretty central idea to a potential gap in any sort of methane emissions simulation modeling. So the blue circle on the left, those are true emissions or leaks, I'll refer to them today. We can never know them. All the data that we have is based on doing surveys, flying over our sites, collecting data, but we're not doing it continuously. There's gaps in that data. Even when you do the screening survey, when you're collecting the data on emissions, you're going to miss things. There's a lot of ways the technology can miss detecting this data, collecting these data on emissions. So what we're working with at the end of the day is that smallest circle on the far right, our detected emissions. So when we run these models, we're representing the big blue bubble by the small bubble on the right. And that's sort of the best we can do. Next slide, please. And I just wanted to talk about one example of why we can have this gap between the true leaks and leaks existing at the time of survey. And that's this example of intermittency. What we've learned recently is that a lot of the big leaks, the big emissions at oil and gas infrastructures, they're not continuous. So it's not, a lot of the big problems aren't just something breaks and it just continuously emits at a given rate. It can start, it can stop. This is really, really hard to model. And if you, for example, were to fly a plane over some sites, take some methane measurements, and that intermittency isn't emitting at the time, that just doesn't exist in your data. So it's just an example of something that LDARSim and many of these other models can't accurately represent. And it's just because we don't have the data. Next slide, please. 2 more slides here. Another idea, and sort of that's more of a philosophical problem. We'll never have an idea of all the leaks out there. But this other idea is around this sort of classic phrase with any sort of models is garbage in, garbage out. Any way we define how these technologies, these methane detection technologies work in the model, that's based on the user. So we can say they work on a very like refined level, or we can high level approximate them, and they're both valid. Next slide, please. So 2 examples of this. A common theme that we'd like to think about or idea is how sensitive is a given technology to seeing methane emissions. There's 2 ways we can parameterize this in the model. On the left, we can say it will see every single simulated methane emission rate that is bigger than 3.5 kilograms of methane per hour. But on the right, we can put this probability of detection curve into the model, and you can see it's 90% probability of detection at 3.5 kilograms of methane per hour. And this is based on something called controlled release testing. So you take these solutions out, you set off controlled releases of methane, and you develop these curves. So this is just another example of models are great, but 2 examples of valid inputs. But the one on the right, when you've taken this scientifically derived curve, you're going to get more quote unquote accurate results. I'm not sure how I did for time, but those are my slides. So maybe if there's extra time, that's great. But that's it for me. Thank you.
Thanks, Brendan. I'm going to pass it over now to Wayne Heikkinen. He's going to talk a little bit about the discrepancies between controlled release and operations and quantification.
Hey, thanks, Brianna. So I'm Wayne Heikkinen. I'm a member of the Sundry Petroleum Operators Group. We had a program for 2.5 years running in Alberta, what is called an alternative fugitive emissions management program. So like Brendan talked about with an LDAR, it was just an Alberta model to the base. And so we ran this for 2.5 years. And to tie in with what Brendan said, the kickoff of the program was to take the model, take the area, and try to design what our program was going to be most effective for maximizing the economics. So what could we deliver on an economic scale that's comparable to a base program, and maximizing the number of emissions that were discovered and then repaired. So that program lasted for 2.5 years, which has kind of led to the topics of today for us is quantification perhaps maybe the right measurement at this time? And then to get into that, there's a bit of a story. Is how does it compare to what the model told us? And so we spent a lot of time looking at performance. Here's the technologies that we used, and for this program we'd used an aerial technology, we'd used a ground-based technology, and then we'd used some handheld technologies. And similarly to what Brennan had said, we had found that we were getting different readings from the different technologies at different times, right? And I think a lot of that is leading us to a problem of intermittency. No matter what the technology is that we were using at the time, it is only a snapshot, right? So it doesn't matter if you're flying the plane over the time and we did some circuits, even aside from the program, we had a little bit of research stuff, and we were doing circuits with technologies. And so we took the same technology, flew it over the same site for 25 times throughout the day. And so the range of measurements from that technology was from 0 to 2,500 cubic meters a day of a release. Depending on the time you flew, and if you weren't doing the circuit and just measuring, you would get a vast difference in what your success or failure of your program was going to be. When we followed that up with metered emissions on that same tank at the same time, the average really was 74 cubic meters a day was what the answer was. So knowing that we can't put meters on everything led us into our discussion around, at this point, is quantification the right measurement? Perhaps where we're at with the stage of different measurements from different technologies, until we figure out how to deal with intermittency and even repeatability of detection, is there a chance that at this time we should just be figuring a way to group our releases into small, medium, and large, and base success on counts? Is a thought. Right, we definitely need to quantify. All of our governments are leading to success measurements that are finite, right? It's a measured number. But perhaps we just need to recognize that we are not there quite yet. And in the interim, there's another way that we could be successful. The important part is that we're still detecting, finding, and fixing releases. That's right. That's still the goal, and it's still achievable that way. One of the other things we're going to talk about, or wanted to bring up and discuss, and it was evident in was agreed that, or not agreed, but it was displayed at a conference we'd recently went to down to Fort Collins and seen the methane conference down there. And it's further to the rate is there's just a discrepancy in methods, right? If you have what you see in controlled release testing, the display had said that you can't repeat that in operations, and we're not understanding why just yet, right? Take the same technology, it's proven, it can detect, it runs through the probability curves that Brendan showed, right? So it gets an answer there. You move it out into the field, and the results are different. And so is it because we're too controlled in those release tests? It's not comparable when we get out to the field. I don't think we understand what those differences are yet. So anything that we can do in that space to reduce that difference is welcome, and a direction that we need to carry on for. I guess an example of that is in our program, if we used two different technologies, the trend was very clear. Same technology over 2.5 years, the trend was down. Releases that the technology saw was down. Take a different technology, same period, same area, the trend that technology showed whenever we went out was that releases were increasing. So you have one technology, one part of the program showing everything is working well, and you have another part of the program saying that what we're finding is going the other direction. So I think there's just a lot of, right, our view is that there's just a lot of unanswered questions that need to get better answers. And that's what we believe we need to keep working on and to tighten the gap. So thank you.
Thanks, Wayne. Final panelist, I'm going to turn it over to Adam Heyman, our Senior Manager of Technical Operations at CMC. Adam?
Awesome. Thanks, Brianne. Hi, everyone. Like Brianne said, I work at Carbon Management Canada, where I spend most of my time working on the Alberta Methane Emissions Program, specifically testing and validating the performance of these aforementioned methane detection technologies with the goal of accelerating commercial deployment and use in the alternative fugitive emissions management programs. So the testing, I'll design and execute the control release testing to kind of fill in the gaps that the regulator may seize to get kind of these technologies out there for use and start to reduce emissions. I kind of want to start off here by defining a couple of terms that we've kind of been alluding to so far, but just so we have the same definition here. So when we talk about a technology, that's the gas sensing instrument itself. So you can think of like the metal oxide sensors or a TDLAS or like a CRDS or OGI sensor, something like that, that's optionally configured with a deployment platform and or like additional instruments like GPS or wind. So like the technology, this is what is collecting the emissions data. And then when we talk about a method, this is the technology combined with a work practice and analytics for use in an LDAR program. So a method has to clearly state any mandatory actions to be performed as part of the work practice, along with suitable operating conditions for the technology. So these include like environmental conditions, can you fly over snow, things like that, limitations on facility types, technology configurations, and survey procedures. So why this is important is because a method can change a lot with the technology. So an example could be if you're validating the performance of an aerial method or looking at the data collected from an aerial method, you may want to test several altitudes and speeds, and each configuration and set of deployment parameters would count as a different method. So this is important as each method will have different performance metrics. So your minimum detection limit for an aerial method would be lower or better performing for like the lower altitude and speed configuration. But then there's like the economic trade-offs, which Brendan alluded to earlier, like you can fly fewer facilities. So where's that right balance? But the key is having that defined method so you know what you're testing and then also what data you're looking at. And on those lines too, like how do you know a method was deployed as tested? Well, you need the right data. So as part of the Alberta Methane Emissions Program, we kind of based our data requirements on existing voluntary initiatives and standards, such as like the Veritas standards from GTI Energy, specifically the measurement and data collection guidance. So if you want to look that up, you can kind of see how the different LDAR activity data fits together and where like you might have some gaps. And another term here is kind of bottom up. So this combines like your estimated emission rates from individual sources to achieve like a total wide system estimate. So these inventories are based on direct measurements, engineering calculations, manufacturing data, and emissions factors and activities. So you could say like I have X number of pneumatics on my site from manufacturer A that emits this amount. Then you add in your compressor data and other kind of equipment data to get this bottom up inventory. So why this is important when it comes to measurement discrepancies? Well, like methane emissions reduction, it's a complex issue. So your sources need to be identified and monitored, and emissions need to be measured, quantified, recorded, and reconciled from top-down sources like your drones, aircraft, and satellite, and bottom-up sources in order to like get a starting point for effective mitigation strategies. So you can't really build an effective strategy till you know exactly what you're looking for or what you already have. And so you've probably heard the term reconciling a lot in the methane emission space. So this refers to combining top-down measurements with a bottom-up inventory to kind of get an improved or more informed emissions estimate. And so I think we've all seen it a lot. These independent methane monitoring studies have shown like significant discrepancies between the measured quantities and the emissions details recorded by industry and in like the provincial and national inventories estimates. So like on average, we see measured emissions are 60% or higher than those reported in official inventory estimates. So why this is important is because there's more and more emphasis on measurement-derived inventories and policy. There's no substitute for direct measurements. So like OGMP and MIQ require measurement-informed methane reconciliation. On those notes, like you can't manage what you can't measure, but then don't measure what you don't plan on managing. So like if you're not going to do anything about your tank thief hatches or unlit flares, like if you're not going to add a different combustor or a controlled system on your tanks, then I don't know what you're really accomplishing by doing all these measurements. But so going into the different measurement discrepancies, like so you can have multiple measurements from different methods telling you vastly different things. So with methane fees, like carbon taxes and credits, this becomes extremely important. So most studies that have highlighted this measurement discrepancy between like the top-down and bottom-up inventories have relied on a single screening method compared to bottom-up inventory estimates. So you can think of like an aircraft flying over and then comparing that what they saw with the bottom-up inventory. But what happens when you have multiple screening methods all providing like wildly different estimates? So an example might be from the US, you have your carbon mapper or satellite or aircraft measures X and reports into some kind of whistleblower campaign or system. But then you recently performed an OGI survey that shows estimates of or emissions of Y. Like how do you know which one to use for reporting? And then how do you scale the measurements from these screening surveys, which are really like an incomplete snapshot in time across an entire company's asset base? So what number do you use? Like we need a transparent and coherent methodology for how do you actually get to a measurement number you can trust. So how do we bring these disparate measurement sources all together to perform an apples to apples comparison? Like we need to reconcile among the different spatial and temporal scales and use that data for transparent and trustworthy reporting. So this is something that is getting more attention, but it's still not quite, there isn't enough consensus to really expand it across the board there. So it's not just the measurements and associated accuracy or validity that are important, but also the method for interpreting the data. So one example of this would be a recent study of satellite data where 4 different expert teams provided their analysis of the same data, and all of which came up with very different answers. So the data collected from these technologies by itself doesn't really provide a lot of insights. We need that coherent methodology for how do you take that data and turn it into actionable insights. And I mean, they're all different results that they got in the study. So it's not to say one is right or wrong, but we just need that consistent interpretation. And this kind of leads into the second topic I want to bring up is the siloed data. So oftentimes we the GHG or emissions departments and companies are under-resourced, or a few people have to shoulder a tremendous amount of work. So these teams are often siloed and unaware of what each other is doing. So I think of a bunch of the companies I worked at in the past, sometimes engineering and subsurface, no one really talked to each other, even though you're all on the same team. You should probably, start to figure out which data you need or what do you have already. So that kind of leads into like, there's a lot of information and tools that you already have. So an example would be the engineering and process data that you can combine with your emissions data to give you a better understanding of your overall picture. So an example would be if you have thermocouples on your flares and they're cold, but there's pressure going up there, you probably have an unlit flare. So it's using this data that you already have to start deriving insights and maybe improving your operational practices. So you shouldn't need the latest shiniest thing or technology to start improving today. Like you have the data there, most likely it's just kind of bringing the ops team and everyone together to kind of figure out what you already have. So, and on those same notes too, there needs to be a stronger relationship between the vendor of technologies and the operator. Like they both need to lean in to better understand each other. Like what do we have? What do we need? What are the data types and processes? How do we line this up with operational data? So like, is the data showing that there was an unloading event or something like that, just so you can get a clearer picture of what's really going on. And then that'll help you optimize deployment for your specific use case and asset base. So I'm gonna do it for time. So while performing all this measurement reconciliation, you can't lose track of what the goal is, which is what Wayne kind of pointed to as well, is to understand and reduce emissions. Like you need to shift your mind, focus from reacting to emissions in terms of like that would be your typical LDAR program, to understanding and preventing emissions through the integration of various teams and operational data. I think that's my high level there, Brianna. It's mostly more questions than answers.
Thanks, Adam. That's usually how I feel after I meet with you, more questions than answers. I am reminding everyone that if you have questions, you can add them to the chat at any time. I have a few of my own. I think you guys outlined a lot of the limitations from modeling, the limitations of some of the technologies. But if I'm an operator and I am just looking at what the regulations require, why would I consider doing something alternative? And sort of what are the current limitations of the technologies or the survey frequencies that would drive me to do something different? That's a question for all three of you. Maybe I'll start with you, Wayne, since I know you have the most experience in that alternative measurement programs.
So I think specifically in Alberta, like why would a company consider an alternative to the regulated way right now? Is it provides some opportunities to use new technology to take advantage of things like what Adam was just talking about, engineering solutions, right? So if you have a method of tracking data and measuring things built into your sites already, why are we having to go out and measure something different if we can measure and record already? So it's a way to use existing stuff. It's a way to find imaginative solutions or technologies that let you get the job done faster. Aerial, for example, lets you survey a large area in a short number of time to find emissions and react or to deal with them, right? So I think it's right. Different technologies are suited for different reasons, and there's different ways to get to the answers. So I think companies are always looking for ways to be innovative, to find newer technologies that can provide, and different methods. To Adam's point, I think it's a combination of the technology and the method that allows you to get more rapid, bigger areas covered in shorter amounts of time, which then can lead to turning around and maybe higher frequencies.
You can maybe do it more affordably with different technologies and different time frames.
Yeah, once you maximize your solution, I think this is kind of what.
Brendan, do you have anything to add?
Yeah, for sure. I guess like maybe one quick like note when Brianne mentions like the current regulatory requirements, I said it really quickly, but it's almost always based on a boots on the ground survey of your assets with a handheld technology to look for emissions. The standard one these days is an optical gas imaging camera. It's essentially a thermal camera. You can see the plumes in the camera. With those, and if you do those in Alberta, depending on your site, once or 3 times a year, you're good. You check your regulatory box, you did it. But there's been a fair amount of just sort of peer-reviewed studies that have come out that says like there's limitations to these sorts of surveys. You might miss leaks for a litany of different reasons. If it's the operator themselves, it's just, it could be complacency, it could be the types of emissions that you're missing. So what these other technologies can often give you is just at a really basic level is a different way to look at emissions. And Adam touched on this. The cameras themselves, these OGI cameras, that's what we refer to as bottom up. If you're flying a plane over a site, that's going to be your top down. You're just seeing sources differently, which is a really simple way to think about it. But this seeing sources differently piece of it is important because the more different ways that you're seeing sources is the more holistic image of your total emissions that you're getting. And then we start to move towards that reconciliation idea when you're getting those top-down measurements and your bottom-up measurements. One thing I do want to be, maybe I don't want to rock the boat too much, but it's hard to do it more cost effectively than just doing your OGI surveys. It has to be right now where we're at in the industry. It's mostly operators who are trying to do some sort of voluntary initiative, like the OGMP 2.0 or Veritas. And it's because we're at the bleeding edge right now. We're learning a lot. And so we're still sort of at a place where it almost has to be voluntarily a little bit. So, yeah.
Oh. Adam, do you want to give us a sense of what those new technologies might be that you would use in an Alt-FMP?
Yeah, that leads to maybe one of the barriers of kind of applying or rolling into an Alt-FMP is the capacity. Like people at these companies not these companies, but in general, don't have the ability to keep up with it all. All the new things that are coming out, like Brendan alluded to, there's 200 plus methane detection technologies out there. How do you pick the one for you? I mean, you go to these trade shows and everyone will say it's the greatest thing for methane emissions, which great. I mean, I would probably say the same thing too if I made something, but it's how do you navigate that space and like what is the optimal deployment strategy for these particular technologies? And what we see a lot is nobody wants to be first. So if there's already approved Alt-FMPs, people will generally look at that and it's less risky for me to kind of follow along and use the same work practice and survey scheduling that's already been approved. I guess for those that aren't familiar with the process in Alberta for an Alt-FMP, you apply to use these alternative methods with it could be a different survey frequency. It's an alternative to your regulatory prescribed kind of method there. So it's a lot of legwork at the front there to do the application, and then plus there's the additional data and managing that. So I mean, if a company already has all of that in place, I get why you don't want to kind of switch things up or kind of stick your neck out and say you need more funding to try an Alt-FMP. But like Brennan said, where that I guess you want to call it a carrot or something like that is the voluntary initiatives and that market there. Like you're doing it for not just regulatory compliance, but you're kind of going above and beyond. And then to answer your question about technology winners and stuff like that, the short answer is it depends. Depends where they've been third-party validated and tested, what your asset distributions look like. Like Wayne was saying, some people just go for the faster aerial surveys, but then there's limitations associated with those. So it's kind of finding that right mix, which is why it's resource intensive to kind of navigate this space.
There's a question in the chat that I think feeds into this technology piece about if you could just set up cameras to monitor your site 24/7. So could you just use passive monitoring? Why not do that? That seems easier.
That's a great question. I'll take this one for sure. So yeah, 100%. That technology exists. I'll name drop some vendors. There's a company called Kuva that does that. It's an OGI on a stick, and Clean Connect does something similar. So both these companies have a degree of computer vision, deep learning built into their algorithm. So there's a computer that's looking at the OGI feed that's coming in, which is pretty cool. But I guess if folks think back to the sort of circle diagram I showed, and like it gets smaller as you go from the left circle to the small circle, you can stick a continuous monitor on a site and you can still miss stuff. And for a lot of reasons, I'll give a couple. Sometimes they can struggle with seeing methane emissions that go up. Methane's light, it goes up into the air. Continuous monitors can miss those potentially if they're not set up well. another really big problem and challenge that they're all working on, don't get me wrong, like these solutions get better every day, is noise. And by noise, I guess I mean statistical noise. So if you set up a continuous monitoring solution at a gas plant, there's just so many emissions going on at a given time. It's really hard for them to say, this is a leak you need to go address versus this is just the gas plant being a gas plant. And so without that sort of differentiation, that classification piece of it, yeah, it becomes really challenging. And maybe the third one I'll touch on is that's gas plants, that's great. But if you just want to set up like a few, always look at your sites and your well pads, to be honest, a hurdle is cost. These are not cheap solutions to install one of these towers with a continuous OGI camera. And if you're an operator that's watching your costs and you only have to go to these well pads one time a year with the person with the camera, it's hard to sell that installation fee. But yeah, good. They exist for sure. Yeah.
I know you mentioned Alt-FMPs are probably not we're not saving money by doing them yet, but are they working? Are we reducing our emissions by looking at things differently?
Sure. So I think that's a great question, and I will say in one regard, yes, they're working, right? Anytime that we have folks out looking for emissions, finding them and doing something with them, that's a success, right? So we get out there. To the other part of it is how do you measure success? If it's measured against the model or your expectation, then we get into all the finite measurement differences and discrepancies that we've talked about, and it's harder to put success that way. So I think I think the more people we have out looking for leaks and ways to reduce, either by fixing or finding alternative solutions, like, design solutions to emissions using different infrastructure, different things, I think the programs are a success that way. To say it's a hard, here's the line and we're above it or below it, brings into play everything else that we've talked about, whether it's from the initial modeling piece to the differences and discrepancies in measurement that exist right now.
I guess I can follow up a bit on that. Yeah, we don't know for sure, like Wayne was saying, like, well, how do you measure success? And that's part of one of the goals of the Alberta Methane Emissions Program, is to gather the data we need to answer these questions. So we'll be looking at, so like Brendan was talking about, you do the simulation modeling, which is what a lot of people do as a prerequisite for Alt-FMP approval. You look at what your kind of baseline emissions would be, what your emissions with your regulatory prescribed method would be, and then you compare that to your different Alt-FMP deployment schedules or work practices. So what we're doing with the AMEP is gathering data from all these Alt-FMPs to be able to look back and answer the question, like, is this working? How close is it to our predicted results? Answer some of these questions, because up until now, we didn't really gather the right data to answer these questions from like the first round of Alt-FMPs, which, to be fair, the goal was to get more technologies out there and trying these things out. But now it's about measuring performance and kind of seeing if we can answer these questions and where any gaps might be.
Maybe just one last note there, and I think Adam touched on this, and I really agree with him. There's only a handful of jurisdictions in the world that allow for alternative technologies to be approved for use in lieu of these OGI cameras. Alberta's the only place in Canada, besides, like, there's a federal allowance, but Alberta, it's quite streamlined, to be honest, for a government thing like this. And so Adam's right. It's not going to be perfect, but it's so important to get these technologies out there, and for us to start getting the data. That's the big piece of all of this, is once this data starts to come in, we can start to understand what works, what doesn't. And then I touched on this with the continuous monitors. If there's an avenue for them to be deployed and start just getting better, all the technology will get better. So it's hard to say right now, because it's like I mentioned, it's still kind of early days, but all I can say is it's important that we're working on it and trying stuff.
There's another question here in the chat about the scope of emissions that we're including when we're looking at modeling. So I don't know who the best person is to maybe help high level define scope 1, scope 2, scope 3, maybe scope 4, and then what part does LDAR-SIM focus on? Brendan, maybe?
I can talk about what LDAR-SIM focuses on, but I will bungle the scope definition. So if someone wants to take a stab at that for me, I'd appreciate it.
That I'm trying to Google it. I can try. You guys can correct me if I'm wrong. Scope 1 is before your site, so any of your utility needs coming into your site, whether your power grid is clean or not, all of that is part of scope 1. Scope 2 is your actual production, right? Scope 3 is the use afterwards. Scope 4 is even further down the line.
Yeah, I think the question was around scope 3 specifically.
Right.
Yeah, and LDAR-SIM would be, if I'm understanding correctly, it's yeah, for sure. So LDAR-SIM does not think about that. And LDAR-SIM, to even drill down a little bit further, within, I would
Scope
believe,
2, right?
yeah, within scope 2, it thinks about our routine and our vented emissions, but it does that at a pretty high level. So it's primarily focused on fugitive emissions, so leaks. That being said, we're always working on it and we want it to be better, and we kind of are moving it to a place where you can more think of it as like emission simulator, because I'll give a quick example. So if there's a vented emission, if there's an emission at a site that's allowed to happen, that's part of oil and gas. You're allowed to emit a certain amount due to some processes. That's fine. Say you're flying a plane over a site. The plane can't tell what kind of emissions it is. It'll just see that there's a venting emission. The plane will see there's a venting emission. They'll tell their operators, we saw something, you gotta go check it out, you gotta follow it up. And then it'll sort of kickstart this process that doesn't really need to happen. All this is to say, it's important to model all the emissions in site, and we don't do that perfectly, and that's somewhere that we're trying to head.
Thank you. Where is attention most? Is there certain technology development that's lacking behind others? If we're talking about surveying and quantification, even machine learning, passive monitoring. We've talked about a lot of different types of technologies. Their attention needed in one area more specifically, or in overall cost reduction, collaboration, sort of what would your guys' focus be?
I think at this point we've sort of established all the different classes of measurement detection technology, to be frank. Like we're putting them on planes, we're putting them on trucks, we're flying satellites, we're sticking stuff in the ground. We're pretty much, I think, I can't think of that many novel solutions. Potentially I have heard of people exploring different handheld solutions. So instead of the OGI camera, you're holding something like handheld LiDAR. So you're doing LiDAR handheld, which could be interesting. So there is still new stuff coming, but I guess like one thing I can say here is that so many of these solutions, the value proposition is the algorithms and is the machine learning. A lot of these continuous monitoring solutions, the technology in the box, it's kind of rudimentary, to be honest, to a degree. But it's what they're doing with it, and plume modeling. So thinking about like, where does methane move through the air? Like they're running all that stuff in the background. That's sort of the arms race a little bit. Whoever can figure that out really effectively and really accurately, that's the important part.
Yeah, that's a good point, Brendan. There's like a limited number of technologies, but it's the method itself, like what's going on in the background that makes them unique. And I would second that. There's a lot of emphasis on these handheld methods that could be used as an alternative to OGI for that follow-up piece. So usually like in an Alt-FMP, you'll have like a screening activity, which is like your rapid site screen, like an aircraft or something, that alternative. And then you require some kind of boots on the ground or close range follow-up generally. And so typically that's been with OGI, and there's only a certain amount of them, handhelds types out there, and they're really expensive. And as we see kind of required survey frequencies go up, or more facilities are in scope as regulations change, there's going to be an increased demand on the use of these services. So are there more cost-effective methods for that handheld kind of follow-up piece. I know there's been a few coming up, like Brendan alluded to, like handheld LiDAR. Can that be used in lieu of an OGI at a fraction of the cost? Maybe there's some promise there, but it's just kind of taking that data and the back end, the algorithm, and turning into some actionable insight or something that can be used for reporting or be it compliance or kind of differentiated product. So it's kind of, yeah, I'd say that's where I'd be focused on, is that handheld piece there to fill in the follow-up gap.
And I would just add that from an overall perspective, I think collaboration is like we can't do this in silos. We learn more together. And then why do we have to keep relearning all the things, right? So if we can get way better at the collaboration space, what works well for someone else doesn't have to try and experiment that way. We can learn from each other and get solutions, whether it's frequency or finding the right technology for certain situations, what works best. So in my mind, collaboration is a big key to moving faster in the right direction.
How do international policies impact Canada's methane reduction efforts, or do they?
I'd say indirectly, like, I mean, we've seen more of a push from certifying like an entire supply chain out of the US in terms of like their global export into the EU with carbon tariffs. So that's kind of a bit of a driver there. Like if you can't certify your carbon intensity of your product, then you're likely not to pay premium and taxes and things like that. So there's kind of like a flow through from that as like a one of the drivers. And then we tend to Canada follow closely what the US is doing. I mean, generally. So they've had their recent reg updates, and then ours are coming down shortly. I imagine they'll look fairly similar. So that's generally how they kind of interplay together.
Does the fact that Alberta is one of the only places to allow for alternative programs impact international partners, or are other people looking at if they can learn from our Alt-FMPs?
That's interesting. I'm not sure. In the new, yeah, that's funny. In the new proposed supplemental methane rule from the EPA, they've created what they refer to as technology matrices. So they've done a bunch of simulation modeling, and they're saying instead of 4 times per year OGI, you can do planes with this detection threshold X numbers of times per year. And then there's an interplay there, right? If you fly a lot of times with a low detection threshold, it's ostensibly similar to flying a few less times, but with a really sensitive technology. And so they've done all this modeling and they've built out what this looks like. So yeah, I would like to think that these jurisdictions like Alberta and Colorado that had these regulatory avenues in place have informed where the whole of America is heading. But yeah, as a whole, we're moving to a place where it's going to be easier to get alternative technologies approved. I think that's a general, something I can say.
So there's a couple questions from the chat that I'll ask here. One is about any technologies on the horizon that might make the biggest impact. Anything we haven't talked about that?
I think that kind of goes back to like the handheld focus and kind of that follow-up. I think that's the big one there, and kind of what Brendan was alluding to, like the algorithms are constantly improving in the back end, which can be kind of applied to multiple different methods, kind of depending on how they're going to be deployed. So I think the main one is kind of that where I see it is that the handheld to replace or help with the follow-up kind of demand.
Anything different to add there, Wayne or Brendan?
I don't think there's emerging technologies. I think they're just going to all keep getting better the more they're in use, and finding the best where they apply themselves the best is going to be the learning, right? How to use them.
Absolutely. Yeah. And just in a past life, I did some data science stuff. And the way these models work, I'll talk about the two technologies I talked about earlier, Clean Connect and Kuva. I mentioned computer vision. I'm going to use some buzzwords here, which is kind of a neural net. People love that sort of stuff, deep learning. And the way these things work, it's just the more data you throw at it, the better they get. So like the more images of plume, not plume, plume, not plume, plume, not plume, the better the computer will get at seeing if there's a plume or not a plume. So yeah, as long as they're turn their knobs correctly, they're just going to keep getting better.
Like it. One last point before I turn it back over to Shannon. Why are we monitoring methane? Why is it so critical? We probably should have started with that one. Sorry, everyone who joined.
I can take a stab. It's a really bang for your buck short-term win right now. Methane has a global warming potential of around 28 times that of CO2 within a 25-year time span. So if you are stopping it aggressively, it's like buying us a lot more time, bang for your buck, for climate change.
I also like to remind people that it's a product that is easily sold. It's not like reducing emissions that you have to find a market for. Methane has a market already. So yeah, that helps. Shannon, back to you.
Awesome. Thank you so much, Brianne, and thank you to Brendan, Wayne, and Adam for joining us today. I'm just going to share my screen as we close out here. So again, this is Climate Connections. We have our next session on November 29th, focus on different issues surrounding water. It'll be a very similar format with industry experts pitching their pain points and how we have the opportunity to come up with novel technologies or novel solutions for these, all working to fight climate change. So thank you so much for joining. And again, thank you to our sponsors, Entrepreneurship at UBC, Simon Fraser University, and the University of Victoria Impact Investing Hub. And thank you again to Brianne, Brendan, Adam, and Wayne for joining us today.